Welcome to this presentation of the Rotary Club of North Bethesda, Maryland, USA. Our club was established in 1974. We meet every Friday morning at 7:45 a.m., and we often invite guest speakers to give presentations on all kinds of interesting subjects. Please contact us through our website at nbrotary.org. And thanks for watching. Our speaker today is Dr. Stephen Rockower, MD. He is a retired orthopedic surgeon in Bethesda who has become enamored of paleontology over the last 10 years. With the recent opening of the Smithsonian National Museum of Natural History's Deep Time Fossil Hall, he has enlarged his interest in human bones to bones over 500 million years old. Dr. Rockower is now going to give us a virtual tour of the new Smithsonian Museum exhibit.
And that. So if you remember, this was where we started last time, in the center of the hall, and we looked in, from there. But then we started at the back of the hall, really at the beginning of time. And let me get to, here's some of the earliest life, as I talked about, in the Precambrian era, with these animal-like plants. And then in the Cambrian time, when everything really started exploding with the trilobites and the worms leaving trace fossils, if you remember, and these little early vertebral things called conodonts that had little segments and a spinal cord. Then we got into the age of the fishes. Let's go over to here, where the fish developed jaws and bones in their fins. And remember, I'm the orthopedic surgeon, so I'm interested in bones. The bones have, a humerus, a radius, and ulna, just like, we might have humerus, radius, ulna, femur, tibia, fibula in the back. And they started crawling out on the earth. And how did Earth get there? Let me come back over to here and come around over to here. I know this gets a little dizzying. I apologize. How did things start coming out on the earth? Not only animal life, but plant life started coming out on the earth, billions of years ago. The first continents were just rock and stone, and then algae and bacteria came and worked on it in the intertidal areas. And this became soil. This allowed plants to start growing, first as little plants, and then bigger plants, and the insects followed. And as I said, then the fish followed. And this is what's called the Acanthostega, which is one of the first quote unquote fishopods. It's not a fish, it's not a tetrapod, but it's somewhere in between, that first crawled out. And various, all of life had to solve a lot of problems being out on the land, in terms of learning how, or figuring out how to stay dry, or stay moist inside and not dry out. And we got skin, how to breathe the air with lungs. Other things have oxygen capability back and forth through their skin. Reproduction was a problem, being out of the water, and eventually they got eggs, and then mammals brought the eggs and fertilized eggs back inside. And of course, the vertebral stuff and the skeleton with the femur, tibia, fibula, humerus, radius, ulna, just like we have. So nothing is new under the sun. It's just changing functions of various things within the DNA. If you think about it, it's the DNA that gets passed along, and this basic four structure of two arms, two legs really goes back perhaps 400 million years, and we carry that DNA with us. The arthropods had to do similar problems of learning how to deal with the water, air, reproduction, and standing tall. They have their hard shell to keep them moist on the inside. They have pores, flies, and some of these. This obviously is a type of crab that's inside that still has gills, but other types of arthropods, ants, and spiders, all have little pores on the outside to transport oxygen and carbon dioxide, reproduction, and standing tall. Plants.
Question.
Yes, go ahead.
So, with all these challenges of coming out on water, what's the advantage to getting on the land for the arthropods?
For the arthropods?
Well, for anything.
I would think nobody knows for sure, but it's a nature abhors a vacuum. So if there's something that's able to be utilized, go do it, and find a way that it works. And how does evolution work other than a mutation happens that maybe is a little bit more advantageous, and that gets passed down to the offspring.
Maybe the ocean got crowded.
Well, and that was one of the other things as far as the arthropods, or as far as the fishopods, take Acanthostega and Tiktaalik as the early ones coming out, is trying to escape predators. If there's no predators up on the land, then you're the king of the hill, and you get to do what you want. So that's always an advantage, and there may be food out there and other plants and maybe insects to eat, and go ahead and do it.
Okay. Just don't dry out.
Just don't dry out, and as you said, there are a lot of physical things that had to be changed for them to come out. As I said before, that the skull structure had to change to withstand gravity. A circulatory system had to be better developed, kidneys, digestive system, nervous system, even hearing. Fish have what's called a lateral line on the side of their body to be able to listen to vibrations within the water. That doesn't work when you're out on air. So they had to develop some sort of a hearing capability. And again, they were repurposing other things. A lot of the little bones inside your ear are actually old jaw bones, and that's one of the distinctions of mammals. When we eventually get to mammals, is that we're the only ones that have 3 bones in our middle ear. If anybody remembers, I know the doctors do. At least I hope Steve does. Incus, malleus, and stapes. The third one, the stapes, is actually a modified jawbone, and mammals are the only ones that have that. So moving along quickly, so we can get into the real stuff. Then came the Carboniferous times, where there were a lot of trees that died into the bogs and became coal, and I'll quickly go along on that. And then we get into Permian times, where there was a lot of oxygen, and we have our friend the Dimetrodon, who looks like a dinosaur, but it's really not. He's a pre-mammal because he's what's called a synapsid, with one hole behind the eye socket, as opposed to diapsids, which all the reptiles and dinosaurs were. So this guy was really a pre-mammal because of the the one eye hole, one hole behind the eye socket. And again, the bones, there's a nice elbow with a, ulna, radius, humerus, femur. Anyway, and at 252 million years ago, most of what's now Siberia basically became one giant volcano, or multiple volcanoes. And that's where we're going to spend more time starting today, is in this end Permian extinction, because this was really the worst biologic event in the history of the Earth, because with the amount of smoke that went into the air and sulfur dioxide that dissolved into the water as sulfuric acid, 90 to 95% of life died. So all of these things that were nicely living, all the dimetrodon and the trilobites and all those things, they all died off. So there was a very small amount that, once the volcanoes slowed down and things started stabilizing, there was a little bit of life left in the ocean and on the land, and that's what eventually turned into more stuff. Nature abhors a vacuum. So here, the few things that lived said, "Oh, look what we got here! We got new stuff to do." So off they went. This guy called the Lystosaurus is actually good, because he's another on the mammal lineage. He's not a mammal, but this guy became a mammal, as well as some of these other things in the ocean and various plants. So the major predator at this point in time, now we're in what's called the Triassic area, which is the first part of the Mesozoic era. And this was probably the major predator at that point. He was it's called a Smilasuchus. It looks like an alligator, and it's somewhere along that that type of evolutionary tree. Is not exactly an alligator or crocodile, but they're related. And some of the mammals were coming along at the same time, and that's how big they were. You can see this is, maybe 2 inches at most. This is a larger mock-up of that. And they can tell it was a mammal because of the jaw structure and the type of teeth. And as I pointed out before, when people ask, are these bones, the real old bones, or are they, fake or mock-ups? As you look at all of the skeletons, the ones that are sort of attached around the outside with these little pegs around it, sort of like holding a jewel, these are the actual old bones of 250 million years old. The ones that are just drilled into, these are the copies of other bones. So you can tell the difference, as you're looking at that. Okay. So things were growing on the land and in the ocean. Some of these vertebrates started really, going back into the ocean, and obviously they got to be pretty big. There was a lot of oxygen at that point in time, and things were able to grow big. The fish, this isn't a fish. This is more of a dinosaur type, not exactly a dinosaur. Dinosaurs, the definition of a dinosaur has legs that are directly underneath it. So let's go back to the Smilasuchus. That looks like a, where's that Smilasuchus? Smilasuchus is there. You can see that his legs are not directly underneath. His legs are off on the side. So being off on the side, that's really not quite as efficient of way of walking. So that's not technically a dinosaur. He's old, but he's not a dinosaur. So things were rebuilding inside the ocean as well. Obviously, the fish came back, the corals came back. Some of these air-breathing early mammals came back as well. And then at the end of the Triassic, there was another extinction at that point. I think that related to an ice age, and then we get into the real Jurassic time. In the Jurassic time, this is a Stegosaurus, which may have been was my kids' favorite dinosaur when they were growing up. We always had a little stuffed animal of Stegi. They had a lot of plates. This is bone that was on the outside and maybe covered with some sort of skin or something, with these sharp spikes at the end of a tail that it went and hit other things. And obviously, he was somewhat of a predator, and he's fighting on this other guy, looking for his lunch. Everybody's got to eat. And then, as I said, the oxygen levels were bigger at this point. So, we have the Diplodocus, which is this guy, gets to be about 100 feet tall, and the Camarasaurus. These are big dinosaurs. These are now dinosaurs because they have legs that are directly underneath them. So they get to be pretty big. Obviously, they're not carnivores, they're herbivores, chewing on the plants, and obviously we don't have any real fossilized plants, so they have things that may have looked like that, that they were chewing on the upper leaves and things. And 200 and some million years ago, what we think of as flowering plants really weren't there. If you sort of see, these are almost like fern-like things. There were no real flowers at that point. So we had a whole lecture on, on the plant life and how they find out about the plant life, because some of the leaves and things are still there, and get fossilized. And the other things you can learn from the fossils is what was eating them, because different insects eat leaves in different ways. Some eat from the outside, some eat from the inside and leave holes in it. Some bore right in the middle of between the top and the bottom. And so these things are all fossilized, and we can find out when we date the rocks that we find, when the leaves were from, and what kind of insects were eating on them. They also leave things like something called galls, which are, I guess, egg cases of the insects that are there. So, as I may have said before, the Camarasaurus is this big guy, 75 tons or more. And here's his humerus, and that's about, 2.5, maybe 3 feet long, And then there's another humerus that's sitting here of what's called a Brachiosaurus. Now, if this one is 3 feet and this one is 6 feet, if you expand upward of the size of what this animal probably was to have a humerus that size. If an animal like that has a humerus this size, this must have been, 300 feet, 150 tons or more. That's a pretty big animal. How could things get to be so big at that time? How could they hold themselves up? Dinosaurs have a special kind of bone structure that's different than mammals that have air holes and air chambers inside the bones. And that's an interesting clue, because what is the descendants of the dinosaurs is the birds. As we get down to the asteroid and what survived the asteroid, the only dinosaurs that survived were birds, and they have that same structure. So working backwards, we know that the birds and brought this DNA with them to A, to be able to fly, and B, to be able to hold themselves up. In addition, birds' lungs are different than ours, and by extension, the dinosaurs' lungs were different than ours, in that it's a different airflow. Ours is sort of two-way. One goes in, one goes out, goes back through the same channels. A bird, and therefore a dinosaur, have a different type of airflow. It's more of a one-way transit through the lungs. It goes through the lungs and then out a different way to go back out through the mouth. Excuse me. The advantage of that is it makes the lungs somewhat more efficient in terms of extracting oxygen from the air, because you don't have to be doing the same things in all the phases of breathing. It also made the lungs a little bit thinner, and Steve might remember, from his anatomy, that our lungs are separated from the inner chest wall, which is sometimes not good, because we can get air in that space and get what's called a pneumothorax. The birds have lungs that are more attached to the chest wall, because they're able to be thinner and do all that. That's a little bit too much detail for you guys. Let's come back around over to here. Oh, I'm sorry. I want to be. Okay, there. Okay, now I want to come back here. I'm sorry. One thing I didn't talk about too much before was the flying things. This is a pterodactyl, now called a pterodon. This was a relative of a dinosaur, not exactly a dinosaur, and it's not really a bird or any of the predecessors of birds, just because of the way that the arm and the wing structure were, and it's the long extended thing here is I think the fourth metacarpal, the fourth finger. Birds it's the first finger, and so they use that to say that this was really on a different evolutionary tree, as far as flying. But this was the first flying animal that developed that. Didn't have feathers, probably. We don't think that one had feathers. They haven't found any fossils that have any kind of feather-like capability, and I'll show you in a few minutes about the fossilized feathers. But they probably had something, like a membrane or something, almost like what bats have to provide the wing surface. The other thing that I may have talked about last time is the origin of oil. We can get to there. As I've said before, the coal comes from the trees of the Carboniferous time. Oil doesn't come from dinosaurs. If anybody is old enough to remember the Sinclair gasoline company with their nice, cute little green dinosaur on their logo, that's a lie. The origins of oil come from microscopic plankton type things, and billions and trillions of them died in the ocean, fell to the floor, and was covered over and then liquefied, and that's now what the oil is that we are burning and using every day. Okay, where else do we want to go? So as long as we were talking about the birds, let's talk about birds for a few minutes. So here's some of the early dinosaurs that became birds, and they got fossilized, like this, and you can see the feathers. And when they look at these under the microscope, under the electron microscope, you can find what's called melanosomes, which are the little pigment-containing vesicles. So these were, feathers that help them fly, and probably had pretty colors too. Maybe somebody has seen some of the recent reports in the newspaper about a very colored bird that just appeared in the DC area, that's normally found further south. So birds have nice colors on them, and so this is where they came from. Now, how did they develop that? Why did they suddenly start flying? They didn't suddenly say, well, let's go flying today. It could be some of the non flying dinosaurs that had some feathers, and they probably even the T-Rex probably had feathers. As they were trying to escape a predator, maybe as they were trying to jump, maybe they could glide a little bit, and that helped them escape. And as I said, if you have a mutation that helps you survive, that gets passed on to your offspring, and then the next mutation helps you glide a little better. And probably that's how the whole concept of flight happened over obviously an extended period of time, that little by little, the gliding and the changes of the shoulder girdle to be able to flap a wing, and the changes in the body structure to give it the actual lift, took millions of years, but eventually was able to happen. And so here's some of these other early birds that were all in the Jurassic time. The Jurassic time, obviously, no, I take that back. That was in Cretaceous time. Because the Jurassic time is when we get into the T-Rex. Here's Charles Darwin that's sitting in the middle of the museum, because he's obviously an important guy in the whole thing. So everybody gets to take a selfie with him. So here's the T-Rex. And the Tyrannosaurs, again, were the biggest predator. The Tyrannosaurs probably were around even earlier in Jurassic time, but it wasn't until later that they became the major predators. And this extra chest ribs, so to speak. At first, they didn't know what that was, but this is one of the things that made the paleontologists talk about the lung structure that that I talked about, because this helped support the the lungs that were flimsier than our lungs, even though we think our lungs as thin and flimsy. This gave extra protection. So the Triceratops was an herbivore that was pretty big, but he was the the prey of the giant T-Rex. The Tyrannosaurs were first sort of discovered out west, mostly in Montana, in an area called Hell's Creek. It was first, they first started finding these in the 1870s, and maybe people have heard of Edward Drinker Cope and Marsh, were two famous paleontologists from New York who hated each other and sent crews out west to dig up dinosaur bones and to steal them from each other's crews. And so they had things called dinosaur wars at that time in the 1870s and 80s and 90s as these guys were first discovering things. This was time when people didn't really know that there was that life was really millions of years old. Biblical things said that it was 6,000 years old. And where did these come from? Where did how could God allow his creatures to die off? And so obviously this was a very controversial topic through all that. And in some ways it goes on today.
On that, I have a question, if I may. The billions years of existence in the Earth, how long have we been, the human race?
Well, depends on what you mean by human race. The early hominids started.
People like us.
Okay.
Like us.
It's been about 1 million to 2 million years.
Okay, thank you.
And if I have a couple of minutes toward the end, I'm getting close to the end. Okay, so I got to move quickly. So here's one of the other large dinosaurs called a ankylosaur that had this huge thing on the back that would swing and probably crack some ribs. So this is a guy that had some rib fractures. But I got to finish Cretaceous here. I talk too much. So one fine day, 66 million years ago, this giant asteroid hit in what's part of the world. I'm sorry about that. Hopefully my wife will pick that up. Good. In the Yucatan, and that blew a lot of smoke and dust all over the Earth. And we talked about the layers. There's a layer of what's called iridium that they find all over the Earth. Below the iridium layer is all the dinosaur bones and fossils. Above the iridium layer, there are no dinosaur bones or fossils. So they think that that's one of the things that caused or was part of the extinction of the dinosaurs. Why iridium? Iridium is a slightly radioactive substance that is not normally found much on the crust of the Earth, but is found in asteroids. It's found much deeper in the Earth, but that's one of the things. So what happens when that, when a large asteroid hits and blows, has earthquakes and tsunamis and wildfires all over the western part of the United States and South America, and probably part of Africa and Europe, because they were much closer together then. The continents were, continental drift hadn't happened quite so much. There's a lot of, again, sulfur dioxide because where they happened to hit had a lot of sulfur in it. And so acid rain went around. The clouds killed off a lot of the Earth. We only had about 80% of life died that time. And eventually life started coming back over the next couple of million years. You know, what kind of life came back? Mollusks came back. Some of the fish came back. Some of the small mammals came back. And let me come around to the mammals, such as this guy, who became a early primate called a Smilodites. You know, he's a primate. This was, you know, again now getting closer to humans. He had eyes in front of his head. The skull structure showed that the foramen magnum, which is where the nerves come out, was in the back of the skull. As we started getting more and more upright, that started coming on the bottom of the skull. Humerus, radius, ulna. No, stop with that. You know, fingers with an opposable thumb to be able to climb around on things. Where'd I go? Oh, I want to go this way. So the mammals again started taking over and got bigger, you know, including the mammoth, and where is it? The giant ground sloth. Where did he go? The giant ground sloth, which was on Earth, and the you know, the saber-toothed tiger, but also over the last couple of million years, there's this guy that came out, which was humans, and the humans turned out to be one of the worst predators. You know, they killed off all of these big animals. Why did they do that? Because they wanted, you know, a lot of good meat. The problem was that the mastodons and ground sloths and stuff like that have relatively slow reproduction, and when they kill off too many of them, they don't reproduce fast enough to bring themselves back, and so that's one of the reasons that they get extinct. How much did humans cause extinctions? In Africa, 17% of the large mammals were killed off. In Asia, 18%. In Australia, 90-some%. North America, 74%. We've done a lot of bad things, but we're trying. So, so here's where we are. You know, this is the giant sweep of Earth from more modern times back through Cretaceous, Jurassic, and earlier, millions and millions of years that has been on Earth. We're trying to keep ourselves going. You know, life will survive no matter what we do. The question is, are we going to be the ones that survive with it, or is it going to be the cockroaches and bacteria and flies? You know, so we'll stop at that.
Steve, I have a quick question.
Sure.
Weren't there flying insects before flying birds?
Yes.
So,
yes.
But it's not that insects became birds.
No, insects, you know, arthropods, you know, insects that have a hard shell around the outside, they have their own complete separate, you know, evolutionary tree.
Huh. And will dinosaurs eventually become oil?
No.
My whole life is a lie.
Uh, well, what can I say?
I just want to ask a layman's questions. All the transformation from insects to birds or something else to something else, the theories of evolution, is it scientifically proven or just the hypothesis that we are relying on?
No, no,
Especially transform.
okay. This is scientifically sound, um, in that they have enough, fossil remains to trace step by, almost step by step by step of of the the animal tree, whether it's of the vertebrates and some of the early non-flying dinosaurs, and then some of the early sort of flying dinosaurs, and then the better flying dinosaurs that became birds. So they have the progression, and they're able to date um, the ground layer that they're in with various kind of dating techniques, something like carbon dating, but it's called argon potassium dating, among other things that they can date for longer. And now that they're actually able to extract some DNA from a lot of these things and see the DNA sequences, once they get the entire genome, the DNA sequences that are similar from one animal to the next. And so that way you can prove that this became that, in that kind of way. Am I making sense?
Yes.
Well, conceptually, yes, but some argue that we have tigers uh, and we have cats today, right? So their
Sure.
sequencing is pretty similar in nature, but in different shapes or sizes.
Sure.
So could there have been those who want to, I don't have any position because I haven't studied that. So how do we justify that?
Well, it's, they have a common ancestor. It's like we didn't descend from monkeys or apes. We have a common ancestor.
Okay.
So there's an ancestor back there, and I have another part of the whole tour on human origins, where they can trace the changes in anatomy and and that, and now with the DNA, that they have the common ancestor, and then things split off. Why do things become different? Different species, when conditions change, such as a mountain, you get on either side of a mountain range and you can't go back, then the two populations can evolve in different directions.
You mean climate actually changed then too?
Oh, absolutely. There've been lots of climate change over the years. Let me quickly show you. I think it's this one.
Let me interrupt real fast. For those that need to go, feel free to drop off. I know some have.
Yeah, I'm
But if we
sorry.
got more questions.
I talk a lot, I know.
Steve, this is Dan. I took a class about a year ago now on viruses, and it seemed to be that people are coming to believe that maybe the viruses were the instrument of our evolution.
It's certainly part of it. It may not be the entire part of it, but there's, viruses, even though they're not technically alive, bring DNA into, into our genome. And so, it's certainly, if it's, a DNA that's helpful, then it certainly helps, and gets passed on. One of the thoughts is that the reason mammals were able to bring their offspring inside and tolerate, this new organism, inside a womb, is because of a virus. There's a particular virus that that has a DNA sequence called syncytial syncytial something or other. I don't remember exactly. But it's very similar to mammalian DNA. There's the sequence that's very, very close that's not found in other vertebrates. So there's some thought that was one of the reasons that mammals were able to bring the offspring inside and change. There are mammals that don't have offspring that lay eggs, like a platypus. So what changed? And there's at least that line of thinking. I'm not sure that that's been proven yet, but it's one of the strong lines of thinking. Talking about climate change, this is the beginning of time over here. Let's see how close I can get. And all of this red area is when there are no ice caps. All of the blue stuff is when there are ice caps. So temperatures have been changing up and down over 4 billion years. So here we are here. This is our most recent ice age, where it got pretty cold, and we're warming up pretty quickly here. So it may be, if we keep going where we're going, that we're going to lose all the ice in glaciers and in the North and South Pole, and we'll just have a water world. So
you've been watching a presentation of the Rotary Club of North Bethesda, Maryland, USA. Please contact us through our website at nbrotary.org. And thanks for watching.